Now, I will be talking about scheduling today. What is scheduling? Well, we have already discussed context switching, which means the operating system basically runs on, let's just say it on a single CPU. So it's running just a single thread at a time. And we have this ready queue, and on this ready queue, then we have a number of threads that are ready to run, okay? And when the timer goes off, and then the operating system has to decide which one of these threads in the ready queue should be picked. Okay, now picking a thread to execute on the CPU, that is called scheduling. Now, what we have discussed was the how the context switching occurs, and let's remember that context switching means that you basically save the state of the current process. So let's see, let's save the state, okay, and then restore the state, and then pick a new thread to run, and then restore the state of the new thread. Okay, now that is called a mechanism, meaning that there's only one way to do this. You save the state, pick, run the scheduler algorithm, which picks the next one, and then restore it. So that there is only one way to do that. Now, scheduling, which is the picking of the thread to run next, which means like among these threads in the ready queue, which thread should be picked or scheduled next. That is what the scheduler does, okay? And that is a matter of policy. We call this a policy because there exists no solution that will make everybody happy, okay? Whatever basically method that we will propose here, it will make some types of threads happy and others unhappy, and this is why we call as a matter of policy. Now, along with the issue of how long it will run, we have to decide on how long the new process should run. Should it run till the timer goes off? Should it run for 5 milliseconds or 50 milliseconds? So that is an issue that we have to decide. And then we have to ensure that every thread gets a chance to run, and make sure that try to prevent starvation as much as possible. Okay, so that is our basically goal with our scheduling. Now let's move on. So we call scheduler as the operating system component that determines which thread to run next on the CPU. Now it operates on the ready queue as we have seen. Okay, it doesn't deal with the waiting threads in the waiting threads. Why? It's because, well, even if the CPU is allocated to the to these threads, it will not be able to execute. Okay, so that's why basically it only operates on the ready queue. Now, when does the scheduler run? Okay, now the scheduler basically runs at uh, in a number of instances. Okay, when does it run? When does the scheduler run? Well, there are a couple of possibilities. First, when a thread voluntarily gives up the CPU, we know that there's this yield command, which is basically the processor by itself. It's saying that, well, I have used my CPU enough, so what I want is, please give the CPU to someone else. This is called yield or yol ver in Turkish. Or when a thread blocks an IO or timer, so that's a case where scheduler can run. When a thread exits, it means that we have to pick a new one, or when a thread is preempted due to timer interrupt. So at these times, which means that then we need to basically the scheduler runs and it operates on the ready queue and picks a new one. Now, scheduling can be preemptive or non-preemptive. Okay. Now, in the preemptive case, it means that we can use a timer interrupt to force a context switch. This is basically to forcefully take the CPU from the current thread and be able to give it to someone else. And then there's the non-preemptive schedulers, in which case, the process must either yield or basically uh, basically goes for I/O, etc. Okay, and then we have this issue of batch versus interactive scheduling. Okay, if the batch system it's non-preemptive, it's from the old days, and so it's basically we will see that no other runs, even if the current uh, thread or process blocks. In the case of interactive, it is preemptive, and other runs can do run if they block. Okay. Now let's note that we talked that making the context switch, that is the issue of that's a mechanism, and the module that does that is often called a dispatcher. So I'll mention it with D. Okay. So the dispatcher module gives the control of the CPU to the process selected by the short-term scheduler. So it switches context, switch to the user mode, and jump to the proper location in the user program to restart it. Okay, and there is a dispatch latency, which is it takes for the dispatcher to stop one process and start another one. Okay, so here's the time axis for this whole thing. So this is the time goes from left to right. So here's our like the thread one is running, and maybe it decides to stop. Okay, it can be because the timer interrupt fires. Maybe the thread one is, goes for I/O, and at that time the dispatcher saves the state of T1. Okay, this is where the dispatcher runs, and once it saves, then the scheduler runs. It picks the next thread to run. Okay, and let's say that it picks thread 2. And once it basically picks that, then the dispatcher is called, and it basically restores the state of the T2, and then T2 runs here. So this is the overall idea. And basically the dispatcher latency is like from here, from this point to this point, this whole duration that we have seen here, that is the dispatcher latency, means it's the overhead of making these context switches. Now, what are the policy goals? Now, the goal of a scheduling policy is to achieve some kind of optimal allocation of the CPU time in the system. Okay, because CPU is the main resource of our computer system. But the question is, what do you define as optimal? Now, to understand this, we need to basically set out what are the goals of the scheduling policy, because you want to be optimized basically serve these goals. So there are a number of basically criteria that can be used, and it will be different for different systems. And just bear in mind that in the early days of operating systems, we're talking about jobs. They can actually be replaced by processes in modern context most of the time. So what are the criteria that we can be using? The first one can be CPU utilization. It's basically the percentage of the time is running user jobs. Okay, so ideally you want this to be 100%. Okay, but in reality it will be less, maybe because all the jobs are doing I/O or some of them are blocked and etc. And then there's the throughput criteria, which is the number of jobs completed per unit time. Okay, so if you have basically completed the 120 jobs over 1 minute, it means that your throughput is 2 jobs per second. Okay, and the turnaround time, okay, that's the duration from the submission of the job to its completion. So if a job is submitted that is at 8:05 and it is completed at 8:15, then it means that we say that the turnaround time for this job is 10. So what you want to do is you may wish to minimize this turnaround time for on average for all the jobs. Or other things can be the waiting time, which means the total amount of a time a job spent in the ready list. This is because the job is ready to be executed, but it's waiting because of the scheduling, because there were other guys. Or the load average, which is the average number of jobs in the ready queue. So this is again, so you want to do that. Or in interactive systems, you may wish to look at this response time, which is the amount of time a request is submitted until the first response is produced. Okay, so in an interactive system, what this means is, for example, when you press a key on a keyboard and how long does it take to get it printed on the screen. Okay, so these are all different scheduling criteria that the scheduling policies should think, and which one depends on the system that we are designing. So possible goals for our scheduler will be, you may wish to maximize CPU utilization. You want your CPU, ideally, you want your CPU to be busy 100% of the time. You may wish to maximize throughput, okay? Minimize turnaround time, minimize response time, minimize waiting time. Now, note that if I want to, for example, minimize response time and maximize CPU utilization, these are conflicting goals, okay? So that this is basically, for example, if you take a batch system and you want to maximize the job throughput and minimize the turnaround time, this is the goals that you want to do. In an interactive system, you want to minimize the response time of interactive jobs, okay? So these goals conflict. That's why we say that this is a policy, meaning that there is no one solution that will make everybody happy. And as a matter of fact, the choice of scheduling policy has a huge impact on the performance that the user observes. Now, we have seen basically what starvation was. Basically, starvation means if you have a process, a thread on the ready queue, we want to ensure that it should eventually gets to use the CPU, sometime within so such that it remains in execution. So schedulers often try to eliminate thread starvation, okay, and this is basically this starvation happens. For example, you have to be careful if you have, for example, a priority-based schedule, and then a high priority may always get to run before a low priority thread, and we would say that the low priority thread is starved. Now you can see this in your daily life. For example, if you want to cross the Eskişehir, okay, because you want to get across as a pedestrian, you will realize that due to the traffic, especially at rush time, it's impossible to find a gap to cross it. Okay, so it means that due to you as a pedestrian may starve, okay, to get access to the road. But starvation sometimes is still permitted in order to achieve other goals. One example is real-time systems. Okay, in real-time systems where, for example, we control robots, we have computers that control robots. Some certain threads must run under a specific deadline. And for example, you have a motor control task, and so you have to send commands to the basically to the motor every 30 milliseconds to effectively steer it. And this is a must no matter what, okay? Because you have this robot moving and you have to send the command and no matter what. And in this case, it may be okay to starve other threads, such that we can achieve this, okay? So here's our first algorithm, first policy that we wish to discuss. It's called first come, first served, which is FCFS. Now, this is also known as the supermarket algorithm. Okay, well, this is actually at least the way I name it. It's basically what you see at your local supermarket. Okay, so here we have our cashier, and she is processing basically different customers on the line. And what happens is she cannot move on to the next customer before the current customer is completely done. Okay, so no matter what, you have this queue, and this is basically what happens. Okay, so it's also called first in first out basically policy. It's used for batch scheduling, meaning that the job runs to completion, and it never blocks or gets context or switched out. Okay, now you can see, you may have observed this. Sometimes the cashier she is processing, say, your batch, and there's some item which doesn't have a barcode. So what does she do? Well, she calls up the person who is in the related department and tries to get the price for that. and this is effectively the input output, the IO of your task. And in that case, all the other guys here have to wait. There is no way. Okay, so like no matter basically how long the IO takes, you get stuck at here. Okay, now in this case the jobs are treated equally. There is no starvation. I haven't seen anybody who was locked up in the supermarket, and as long as you wait in the line you will eventually get out. Okay, now what's wrong with FCFS? So this is the idea that if you have jobs A, B, and C, and this is the time axis, and if this is the then you would first run A. It may contain some IOs, and we will see that like in our scheduling we can have FCFS with IO or without IO. This is the case where we assume that it's either all CPU and no IO, and then once it's finished, then you switch to job B, and then you switch to job C. So what's wrong with FCFS? Well, we have all observed what's wrong with it. It means that imagine that you have like this guy has packed two supermarkets, basically trailers full of stuff, and here is you, and you just have a bottle of water and you want to buy it. Okay, now if this guy is in front of you, then you will get stuck at the back. Okay, so the problem is, we have these short jobs get stuck behind long ones, and there is no way that you can get some early access to the cashier. So that's the main problem. Now note that when we talk about this scheduler, we say that some of them were preemptive and some of them were non-preemptive. And what do we think about FCSS? Well, FCFS, you can say that this is a non-preemptive policy. Okay, that's because you just let the job run until it terminates ends. Okay, and after it ends, then you can only start for the next one. So you have no way, once a job has started, you have no way of preempting or interrupting its execution. Okay, that's the problem. Now we'll talk about our second scheduling policy, which is called round-robin policy. Okay, and this is essentially first come first served with preemption. And what we do is we define a CPU quantum, which is the maximum amount of CPU that a thread can execute without interruption. Okay, so in the FCFS, if you remember that if we have at time 0 job A, job B, and job C, if they're all in the ready queue and you basically schedule them, you schedule job A, it runs to completion, and you schedule job B from the ready queue, it runs to basically completion, and then job C. In the case of round robin, we have this CPU quantum that you can see in here. Okay, so the CPU quantum is fixed, and you let job A run a bit. Okay, and if it's still not done yet, then you switch to the next guy. So it's basically another like a CPU quantum, and then the third one, and then come back to the first one, second one, and third one. Okay, so you basically cycle through the ready queue over and over. And at this time, for example, job B and C have already finished, and after this, it will basically continue to execute job A all the time. Okay, so you can see that as a student, this is a policy that will be very fine. In our supermarket example, it can mean that from everybody in the queue, the cashier processes 3 items per person. So it processes 3 items from me, and then 3 items from you, and then 3 items from the next guy, and so on. So it will cycle through this, and if you have only fewer items, then you will be able to get out of the supermarket very soon. Okay, now here from this example, you can see that the job A, it's basically, let me just clear this again. Okay, for job A, it takes basically 13 time units. Okay, job B and C, okay, takes job B and C takes 4 time units. Now the turnaround time with FCFS, which is basically for job A, it ends at time 13, okay, which is here. Now job B, it started at the beginning, so it's basically the total waiting. Now job B is done at 13 plus 1. So this is mainly you, okay? You get into the ready queue, but only at time 17, at 17 seconds, you're off. And job C, it will be 13 plus 4 plus 4. So it will be basically what's 18, 21. Okay. Now when we add these up, so we have the total turnaround of the turnaround time of 51 divided by 3 processes. So you get this 17 as the average turnaround time with FCFS. Now the turnaround time with round robin will be slightly different, so we can see it here. And job A will end at time 21. Okay, so it takes longer for job A, but job B will be out at 11 and job C will be out at 12. So when you add them up, you get 44, and the mean time is 14.6. So you can see that the round robin policy is basically tends to have a better turnaround time to the processes. Now let's move on to our third policy, which is called the shortest job first. Okay. Now, so in this case, what we do is for each thread or process, we basically make an estimate of how long does it use the CPU, okay, before going for I/O. Okay, so you make a measurement of this, and some processes will be CPU bound, meaning that they'll be using a lot of the CPU and then go for I/O maybe for a bit, and then again when they get it, they will use again a long CPU and then small I/O, etc. Okay. And with our examples to this, for example, say that your compiler, like when you start compiling something, then you'll be compiling for a long time with this intensive CPU usage, and then you may be going for disk access, and after you read something, then you'll again be, using a lot of CPU. And there will be other processes which will be called I/O bound. And the I/O bound jobs are basically CPU. They use CPU a bit, and then tends to stay away that they do I/O for a long time, and another CPU burst. Okay. And what are examples? For example, when you're doing browsing, when you're loading things, it takes a lot of CPU, and then but for most of the time, your browser basically waits in your I/O mode, waiting for input from you. Okay, so that's an I/O bound job. Or when you're like editing something in PowerPoint or presenting and etc. Okay, so as we have seen, like compilers, number crunching, encoding this particular video so that I can upload it, they're all CPU bound. Whereas I/O bound jobs are web browsers, database engine, word processor, etc. Now, how do we predict the CPU burst? Like that's the main thing that we will do. So we can get pretty good guess by looking at the past history of the job, meaning that track the CPU burst each time a thread runs, and then track the average. Okay, so and then we should be able to compute a CPU bound job, and they will have a long burst and I/O bound job. And you can imagine that this is actually not a dichotomy. There are only like so that basically main process basically move in between. Okay, just go back. So here we have an example for shortest job first. Okay, so here we have so we have these three jobs or processes in our ready queue, and these are our estimates of basically their CPU allocation. Now this is kind of a repeating pattern, meaning that the job A doesn't end here. Instead, here it will go for another CPU and then another I/O and then etc. So this is kind of this whole thing that I've shown you. This replicates over and over. This is the general trend. Okay, and we have gathered this based on the statistic that we have basically all its execution right here. So we have basically job C. This is a CPU bound job, okay, because it uses CPU a long time. Job B, that's a IO bound job, and job A is somewhere in between, okay, and they are all in the ready queue at time 0. Now, how will the scheduler work? So as you can see, like the first thing that it will do is in the shortest job first is that it will pick the job that will give back the CPU at the earliest time. So it will be picking up B. Okay, it will pick up B because it knows that after this much of time, it will give back the CPU to the scheduler so that it can schedule something else. Okay. So it picks B because it has the shortest CPU burst here. Okay. Now at this time, you can imagine like at this time the scheduler will run. And what it will do is it will look at the ready queue. In the ready queue, we will have job A and job C. Okay. Which one would it pick for then? Well, job A has a shorter CPU burst. So job A is scheduled and it will run here. Okay. And when job A is executing at this time, well, maybe I'll just basically, let's see. Okay, so at this time I have this like A, B, and C are all in the ready queue. Okay, and at this time when the schedule is running, I have only A and C in the ready queue. Okay, at this time the B joins the ready queue. Okay, and whereas when A goes for IO, now I will have both B and C in the ready queue. Okay, and so I have B and C. So who will be scheduled like from between B and C? Well, B has a shorter CPU burst, so then B will be scheduled. Okay, B will be scheduled, and at this time now A returns back to the ready queue. So I will have A here, and who else? C in the ready queue. So the scheduler looks at A and C. Okay, which one has a shorter CPU burst? Well, A. That's why A is scheduled. Now, at this time, like when we look at here, when A ends, B still has not joined the ready queue yet. So at this time, when A ends, the only B is off, A will be off, so only C will be in the ready queue. As a result, well, C will be basically executing here. So I hope that you get a good idea of how CPU shortest job first works. Okay, and then at this time when we look at here, this time who will we'll have A and B in the ready queue, and it will be executed and as such. Okay, so shortest job first, it looks as such, but what is the issue? Now, in this case, when we schedule C here, you can note that C, if it's long, it will basically then B, A, and B will be remain unresponsive for a long time because basically C is using the CPU all the time. So this is a non-preemptive policy which does which gives priority to IO-bound jobs, but nevertheless, if a CPU-bound jobs ever gets the CPU, then the whole system will basically suffer. So basically, the shortest job first, it's a non-preemptive job, and it will run until it blocks for IO or it exits. It prefers IO-bound processes because, like they have shorter CPU burst and they will do that. And the idea is, a CPU burst, a long one, would basically will hogs the CPU. So let's do the short ones first, get them done, okay? And then by doing this, you can allow their input output to overlap with each other. So it means that you'll be using the CPU more efficient, and your interactive programs typically have short CPU, so you'll be giving them priority and you will have really snappy interactive performance. Okay, now this is nice, and actually in our daily lives we all do this. It's called procrastination. Okay, and when you're faced with too much work, you typically pick the easier ones and then get them out of the way, and leave the big hard tasks for later, like such as your assignment, homework one. It's a big task. Okay, so you first do this and that and this and that, and sometimes you never get to work on the actual hard tasks. So this is a reminder that you should actually really work, start working on your homework one. Okay, now let's look at shortest remaining time first, or SRTF. SRTF, remember that the shortest job first was a non-preemptive policy. Now its preemptive variant is called shortest remaining time first. Okay, and it works as such. So it's, if you look again, are the same task, the same A, B, C processes that we have seen in the previous one. So initially, if you remember that, like at this time, we had A, B, and C. Okay, and if you remember uh, from B, and like the B had the shortest burst. Okay, so it was, let me just draw this. So B had the shortest burst, and it was less than A. Okay, and it was less than C. So see, this was a CPU bound job, and this was an IO bound job. So at this time, well, we pick B. Okay, now when B goes for IO, okay, then we'll have what else? A and C. Okay, and as a result, we run A. Okay, now till now it looked like it was exactly the same thing. Okay, now the difference is, with this A, it was like, if you remember in the previous case, it was about to run as such. Okay, but during its execution of here, let me just delete this. Sorry. Okay. So A was supposed to last like this. Okay, you get the point. Now, when B returns back here, okay, and joins the ready queue, then the SRTF, it looks at the time remaining here. So here we have this basically region, which is the shortest remaining time of A. Okay, the shortest remaining time, say the underscore A. Okay, now we compare this with the shortest remaining time of B, and you can see that in this case, the B is, this is what are basically the maximum here. So you can see that the shortest remaining time of A is greater than shortest remaining time of B. Okay, now at this time, since this is a preemptive policy, what it would do is it would decide that, well, if I give the CPU to B, I will get it back first. Okay, so as a result, it will preempt A, and it will basically run B here. And you can see that it's good, because since it ran B, it would get the operating system will get the CPU back much faster, okay, than the case for A. Okay, now at this time, again, when we look at who is basically still in the ready queue, at this time I will have, well, B is out, so I'll have A, and you'll have C. Okay, and with A I have this much amount. Okay, with A I have this much amount, and with C it's basically way large. So what we do is, when we do that, now we basically execute this remaining part of A, okay, which was left from this part. Okay, so we run A, and at this time, now this is very interesting, I have only C left. B is doing its IO, A is doing its IO, so only C is left. So we schedule C. Okay, now when we schedule C, basically it would do a long time. Okay, let me just do this here. So in the case, if I did not basically preempt this would have been the case. Now, let's see, maybe a little bit less than this. Okay. So at this time, now A returns back to the ready queue first. Okay. Now when A returns back, the scheduler checks again. Okay. It checks the remaining time of C, which is here, shortest remaining time of C, okay, which is this amount. It checks this against the remaining time of A, okay, and if you remember, the remaining time of A was way larger than this, so it says, okay, let's go on with C, okay, and then at a later time, then B returns back to the ready queue. Okay, at this time, so the scheduler runs here with compares, and as a result of this comparison, it realizes that the shortest, maybe I should just say like this remaining time of C is less than remaining time of A. Okay, so it decides to go on, and then here we'll have all of them, like C, and in this case when we look at the remaining time of say B is less than the remaining time of C, which is less than the remaining time of A. Okay, and as a result, at this time it will preempt C, and it will start executing B. Okay, now when B goes for IO at this time, now who do we have? What we have is we have C and A, and if you remember that remaining time of C was less than remaining time of A. Okay, and as a result it will switch to C. Okay, and when C goes for IO, then it will be going for that. Okay, so let me just delete this a bit so it's not short stream, that's the remaining time of that. Okay, let's just delete this. Okay, so let's move on. Wait a bit here. Okay, now let's compare these different scheduling algorithms. Okay, so first let's compare shortest remaining time with round robin. So let's say that we have three jobs, and jobs A and B are both CPU bound, and then basically C is basically a very intractable one. So if we had just a round robin with 25 millisecond time slice, then this would happen, that A would run for 25 milliseconds and C just needs 1 millisecond. So it will do its 1 millisecond, and after that we'll switch to B another 25 milliseconds. And during this time, then C will be doing its IO, but it will not be able to get basically this CPU until here, and so on. Now, so in order to, so it will make our C less interactive. Okay, it's responsible for delay. Now, if I make round robin with 1 millisecond time slice, then you can imagine that, like, C, if I start with C here, when it's IO is done, then it will still be able to get it fast, and etc. Okay, now this looks verified, it remains responsive, and it looks good, but you can imagine that when in these regions here and here and here, you have lots of pointless context switches between jobs A and B. Okay, so, and you can imagine that with each context switch, you lose a lot of valuable CPU time to the dispatcher to just run that. Now, if I run shortest remaining time first, then you can see that, like, it remains very interactive, meaning that whenever C gets out of its IO, okay, when it's available for execution, it will be immediately interrupt all the processes that's executing, and it will be remain very responsive. But in the meantime, you can imagine that in this case, when we start, say, running A, okay, it will continue with A without making any context switches to B, because its remaining time will be less than what the remaining time of B, and as a result, basically, it doesn't make it makes way less context switches between processes. Now let's compare these four scheduling policies. Okay, so let's say that whether they are preemptive or not. So here's the first comes first served. Is it preemptive? No. Okay, this is our regular supermarket algorithm. Round robin, yes, there is a time and interrupt, there's a maximum amount. Shortest job first, no, it's not preemptive. You run it and the processes run until they go for IO, and the shortest remaining time, it is preemptive. And when we look at when the scheduler is called, with the FCFS, this is basically when you call the scheduler only when the current process exits. Okay, and when the current process goes for IO, no. When a new process is added, no, you don't call it time interrupt, you don't care, and etc. In the round robin case, when the current process exits, well, you can imagine that the scheduler is called all the time, so there's nothing to discuss. And when the current process goes for IO, yes, you call the round robin. And you also call the round robin when the timer interrupt goes off. Okay, so when the timer interrupt goes off, then you also call this. Okay, but you don't call when a new process is added or a process comes. Oh my god. In the shortest job first, it's again the same thing, that when the current process goes for IO, you call it. Otherwise, it is non-preemptive. In the shortest remaining time first, you call it as such. But here's the thing. When a new process is added, okay, so when a new process is added to and the contents of the ready queue is changed, and then you again call the scheduler. Now, this allows you that, when a highly interactive the basic process basically gets into the ready queue, you stop what you're doing and you have the ability to switch and execute that at once. Okay, this is very important. Now let's talk about priority scheduling. In priority scheduling, you assign each thread a priority. Okay, in Linux, these range from 0 to 99, and actually there's a nice system call that lets users adjust this. Now, here's something that's funny, that when you do a nice, it takes a parameter, but the scale is inverted, meaning that minus 20 is the highest priority, whereas plus 20 is the lowest. Can you think about what the reason for this? It's because, from your you want to distinguish noobs from pros, meaning that if somebody just learned about this and wants to make his own process run faster, he would automatically do a nice plus 20, and as a result he will get slow as hell. Okay, so there's some funny aspects, there's some sort of humor in the Unix philosophy. So the priority may be set by the user using that, and also as well as by the operating system or some combination of the two. So you may just adjust the priority to bias the scheduler, and the operating system may adjust as well to achieve system performance goals. For example, some system processes that, for example, updates certain say structures in the file system and so on, they may have to run with a higher priority or as a lower priority, and the operating system has the power to do so. And when scheduling, it's simply run the job with the highest priority. That's the job. This is usually implemented as separate priority queues, as I will be showing in the next slide. So there is one queue for each priority level, and you use round-robin scheduling within each queue. And if the queue is empty, then you look into the next lowest priority to queue. Now there's this problem of starvation, which means that if you have a lot of high priority threads, then the low priority threads may end up starving. So this is a serious problem with that. Now let's look at the multi-level feedback queues. What we want to do is, here's our observation, that we want to give higher priority to IO bound jobs because we want to make them to be interactive, and they would need CPU rapidly after and IO. For example, the user does some kind of input output. Now, whereas jobs that are not like like you can note that jobs are not always I/O bound or CPU bound. For example, when you look at your web browser, it's mostly I/O bound, but when for example, it starts executing some code in the on the browser, then all of a sudden it becomes CPU bound. So the idea is you want to adjust the priority of a thread in response to its CPU usage. And here's the basically simple rule to do so. You increase the priority if a job has a short CPU burst. So this is an indication that it is an I/O bound job, and decrease the priority if the job has a long CPU burst. Okay, and you typically declare a certain CPU quantum, which is the maximum amount of CPU that it can have. And if it goes past that, then you basically decrease its priority. And you can see that, and the jobs with lower priorities would get to use longer CPU quantum. Now let's look at that and to understand the rationale for this. Okay. So here we have our multi-level feedback queue implementation. We have three priority queues: high priority, medium priority, and low priority. Now in the high priority, we have two threads that are running, and we basically pick one of them. Let's pick this one. We run it, and then then you do a round robin among these two. So you run this one, and after a certain time, basically you give him a small CPU quantum, but it uses its CPU burst, and then we have to force him, we have to preempt him, okay, to get the CPU back from him. So and then we place it into a lower priority queue as here. And then after that we look at again the high priority queue, and we found the next one, we run it, and again we have to preempt it to get the CPU back from it because it did not complete. And after this, then we run we basically there's no one in the priority queue, so we fall back to the medium priority queue and we run this. And after running him, if this thread runs with a CPU burst, meaning that you give him a longer CPU quantum. So if I look at, let's just draw this for the medium priority, for the high priority queue, the CPU quantum is say this much. Okay, this is the CPU quantum. And for the medium priority, you have a slightly longer one. For the low priority, you have even a longer one. And in this particular case, this guy, he was in the medium priority, so he ran for a bit, but he stopped here right before finishing its CPU quantum, and then he basically went for I/O. As a result, we moved him up into the high priority queue because we realized it is becoming more I/O bound and it has a shorter CPU burst. Okay, so this is the multi-level feedback queue. Just go back. Okay, erase this. Now, along with this, this idea of priority is good, but there is one major issue with this, which is apart from the starvation, it's called priority inversion. Now, this is a problem that might occur in priority scheduling systems, and it's effectively you have a higher priority process that's indirectly preempted by a lower priority task, effectively inverting the relative priorities of the two tasks. And actually this is something that has happened on the Mars rover Sojourner, and there's this basically link in Dr. Dobbs' journal. By the way, this is a magazine that you should go ahead and read. It's something that you'll learn a lot in terms of methods. And so I really highly suggest that you become aware of this and follow this regularly. Now let's talk about the priority inversion. Now here we have is two rods. Okay, one rod that we have here. Okay, here we have basically a cross rod. So we have one rod going this way and another rod going this way. Okay, and we have basically uh, pu- uh, three actors here. One, it's you, a low priority car. This is the top view of a car, if you wish, and this is a high priority VIP car. Okay, and then we have the pedestrians who are using this to basically cross to move across this. Now, this VIP car is of like it's prior to number one top, and then comes the pedestrians number two, and then comes your car, which is number three. Now imagine the case that your car is basically being executed, and again this is a concurrent system, and you can either move only one of these actors at a time. So imagine that you move here, and basically while you are here, then we make a switch. Then the higher priority basically car needs to get the access. He tries to move on, but he cannot move because effectively you have obtained the lock for for a certain resource. It can be imagine it can be a mutex. So it has the mutex. So this guy cannot move in here. Okay, so it cannot proceed. Even if the CPU is given to this process, it cannot make progress because this low priority process has obtained a lock. Now you can imagine that, well, is it for like, can I forcefully take this lock from him? Well, it's not a good idea, because the reason why we get a lock and basically use this mutex kind of idea was that we may be updating certain structures that are basically very fragile. Like it can be a structure in your in the system, like the file system and so on. So if you try to forcefully take the lock from him, then you may end up with basically you may screw up the data that he is trying to update. Okay, and as a result of this, let me see if I can again. Now, in this particular case, uh, since this guy cannot proceed, even if like because it cannot achieve this basically the lock from him from number three, then can we fall back to number two. So here we have this number two. He will cross the road. He will use this. He will enjoy his time. Okay, and after number two, okay, then we can again go back to like in this case the one cannot execute, and you can imagine that despite number one has a higher priority, due to the circumstances, we have number two who is actually executing. So this is called priority inversion, because number two seems to have a higher priority over number one. So this is basically what is happening in here. Now let's basically go through an example here. So this is the time axis as we move on, and we have three different processes. Okay, A, high priority, B, medium priority, and C, low priority. Now let's say that like we have our C, low priority. It acquires the lock for a resource R. Okay, this is like it's a mutex. It acquires the lock, and after that, then A comes. Now it gets into the ready queue, and it basically preempts C because it's a high priority job, and it starts execution. Okay, and while it's in here, then B, the medium priority process, it gets into ready queue, but it has to wait for A because A is high priority. Now at a certain point, well, is it as A run, then it needs the resource R at that mutex, and it wants to get the lock from C. Okay, so it blocks in here. When it blocks here, then B runs, because on the ready queue we only have B here, and so B continues to run. And when B continues to run, it runs and runs, and when it goes for IO, then like, well, A had blocked, so then we have basically C running, and after C runs a bit, and then B's IO finishes, so it preempts C. It runs, go ahead, and it runs as well, And then we have C. C again, after B goes for I/O, then C continues the execution. It releases the lock, and only after it releases the lock, then A can acquire this lock and for this resource and runs. So when we look at here in this particular region, you can imagine that A here is blocked as if it's a lower priority process, and then the CPU is allocated between B and C. What is the solution to this problem? Well, the solution is called priority inheritance, and this is how it works. Now we have C, which acquires the lock for R, and then A preempts him, okay? And then it gets into ready, it continues the execution, and then A blocks on resource 2, okay? Now at this time, since this resource that A was blocking was acquired by C, then we let C run with A's priority until it releases the lock. Okay, this is the case where if you're blocking this VIP car, then all of a sudden the VIP car gives his priority to you so that you can proceed and release the lock. And after you release the lock, then A acquires the lock and offer that resource and runs. So in this sense, the C inherits A's priority, and that's why we call this as such. So this is a solution for the priority inversion problem. Here's another type of lottery scheduling. Basically, it's called lottery scheduling. It's a kind of randomized priority scheduling scheme. And the idea is you give each thread some number of tickets. And the more tickets that your thread has, the higher its priority. And at each scheduling interval, you pick a random number, say between 1 and the total number of tickets. And scheduling means, the job means holding the ticket with this number for whichever thread. Now, how does this avoid starvation? Well, if you give more than 0 tickets to each two threads, even the low priority threads will still have a small chance of running. So there is no deterministic starvation problem in this particular case. So here's the example that we have here. Now we have job A, which has 30 tickets between 0 and 30 numbers. Job B has 10 tickets, and job C, this is the highest priority basically job that we have, it has 60 tickets. So in round 1, when the scheduler runs, it picks a random number and 26. Now 26 is between 0 and 30, so A runs, okay? Now when it goes like for I/O, then you again in round 2 you pick another random number, 65. Now 65 is within this range, so it runs C, okay? And then it goes for I/O. Then you pick another number like random 92. Now at this time C could win, but you can imagine that C is still in its I/O region, so it's blocked. It cannot win. So you go ahead, you pick another number, 33. Now this is again B. You let the B run, and then when it goes for I/O, then you pick another number. Now it's A. So this is the idea that in this scheme, like you give priority in a randomized and probabilistic manner, and this is such that it avoids starvation problem. Another basically scheduling mechanism is called guaranteed scheduling. Remember that when we talk about these issues, you can mix and merge some of these ideas in the actual systems. In the guaranteed scheduling, you want to guarantee about the CPU usage. So if you have, for example, n processes, then you should say that, well, each of them should get 1 over n of the CPU allocation. Okay, so how do you do that? So what you do is for each process, you can compute the ratio of actual CPU time that it used divided by the consumed CPU time and pick the one with the lowest ratio. So a ratio of 0.5 means that the process had consumed half of what it should have had. And ratio of 2 means process had consumed twice of what it should have had. Okay, so in this case you can you can do a guarantee some kind of a fair usage of CPU schedule. Now, so far we have assumed that, the processes are on their own, but in the fair scarce scheduling, uh, it matters basically who the owner is. So if I imagine, as students in the same class, you're sharing the same CPU. If one student runs two processes and the other student runs five processes, then if we treat all the processes as equals, then it means that the second student will get more of the CPU. So in the fair share scheduling, the CPU allocation is split to the number of processes a user has. So if you have spawned more processes from your user, then actually your processes would be allocated less CPU time because they will be split with respect to the number of other processes. So a user running a single process would run 10 times as fast than another user running 10 copies of the same process. So this is the idea behind this. Now we have been discussing this scheduling as if we have only a single processor. But nowadays, even as a single processor may have multi-core. So when I say multiprocessor, it means you can read it as multi-core, or you can have multiple processors, CPUs with multiple cores, and etc. So then the CPU scheduling becomes more complex because you have multiple CPU, and what we do is this homogeneous processors, you can have multiple physical processors, or sometimes you can have a single physical processor, but it provides multiple logical processors. You can have multiple cores. You can even have hyper threadings, which will show up as some virtual cores in the system. In multiprocessor scheduling, the problem changes from the case of a uniprocessor, where we have a single processor, and the question was which thread should be run next. On a multiprocessor, the question is which thread should be run on which CPU. Now, this is the crucial thing. So here we have our basically thread list, the ready list, and here we have our different cores. Now, which thread should be run on which core? So this is a more difficult problem. And what should be the scheduling unit? It should be threads or processes. And remember that in the case of user level threads, then you cannot distinguish. In the kernel level threads, yes, we can. And in some systems, all threads can be independent. Okay, so you can start different threads, and independent user may start independent processes, and in others they may come in groups like make, and which originally compiled sequentially, okay, or sometimes the new ones even starts compilations in parallel, and then you may need to treat them as a group and schedule them to maximize performance. So these are issues that we haven't even touched on, but you should at least get an idea on how the problems that are associated with it. Now, when we do multiprocessor scheduling, actually running an operating system on a multiple processor is actually a tricky thing. So basically there are two different methods. One is asymmetric multiprocessing. In this case, we dedicate one processor, which is the master processor, to run the kernel code, okay? And this handles all the scheduling, so it schedules the user threads to one of the other cores, which are called slave cores. And the other cores here, the cores 2, 3, 4, they are running as slaves, and they run only user code and user threads. So in this case, the master processor has access to the data structures, so it's actually easier from a operating system point of view, and it just says, this particular one will be allocated to run on core 2, core 3, core 4. Okay, so this is what we call an asymmetric processor. In this case, you can see that the master process, all the system calls that are, for example, being issued by user processes in the slave cores, has to be executed on the master. So this does not scale well when the number of cores that we have becomes large. The other option is called Symmetric Multiprocessing. It's also known as SMP. In this case, we have like at least two or more processors connected to the same thing. And in this case, all the cores, like core 1, core 2, core 3, core 4, they are all equal, and they run both their kernel and user code, and as well as doing their own scheduling. Now, as we will see, discuss maybe towards the end of this course, is uh, that means that all of them will be, for example, if they are scheduling, this guy will be running scheduling here, scheduling, scheduling, and scheduling. And you can imagine that the race conditions on, for example, accessing the ready queue will become actually true. Okay, in this case, because we have multiple cores acting on the very same scheduling queue in the main memory. So this becomes a major issue. We'll discuss this later as we move on. So with the SMP scheduling, there is and basically something called processor affinity, meaning that when we have a process and you want to move this process from one processor to another, it's called the migration of a process, then it can be costly because the cache data is invalidated. Okay, and you want to avoid this migration from one processor to another. And typically we have this hard affinity, meaning that when you assign a processor to a particular process, you do not allow it to migrate. It continues to run on this very same processor till it exits. And then there's a soft affinity, meaning that the operating system tries to keep it running on the same processor as much as possible. But if it's not possible, it can move to another processor. So you can see that this is more difficult, but more feasible. Okay, so here's some article that you can read a little bit more about this. Now, in the SMP, basically scheduling, what you want to do is load balancing, meaning that you don't want one processor to have 100 running at 100% and the other cores basically running like way less, like 10%, 20%, and so on. So all processors should keep an eye on their load with respect to the load of other processors, and they should try to migrate the loaded processor to idle one. So we have basically a push migration, meaning that if you are a busy processor, meaning that a processor that's busier than the others, then it tries to unload some of its processes to others. And then there's this pull migration. It means that if you are, as a processor, you are more idle than your other processor in the system, you try to grab processes from others, okay? And typically they run concurrently, but you can see that this load balancing idea, it's good, but it conflicts with processor affinity because you'll be moving basically processes among different processes. And also, like along with this, another issue is space sharing, where you try to run the threads from the same process on different CPUs simultaneously, and this will basically make your multi-threaded program, for example, run faster. And we have real-time scheduling, and especially in physical, basically systems like this Mars rover that you send somewhere, or any robots that we work with, they are hard real-time systems, meaning that the operating system, must always complete a critical task within a guaranteed amount of time. Okay, and typically, if you think about the computer system on board of a robot, this is the case. And the designers describe these requirements, worst case execution time of instruction sequences, and you prove that system response time. And you can imagine that, for example, if I want to control the wheels, controlling sending commands to the wheels of the robot, well, you may have to do this every, say, 20 milliseconds, because when you're moving, there's no way that, if you lose that time frame, you may collide with something else, you may lose track. So bad things can happen. So that's why we want to have these hard real-time systems, okay? And these operating systems that provide real-time basically guarantees, well, they are specialized systems, and in those systems, we can see that some other processes may be allowed to starve because of these hard real-time constraints. And in the soft real-time systems, for example, in Linux has a soft real-time system where it basically makes sure that the critical processes receive priority over the other ones. So this is kind of sufficient, but it doesn't provide any guarantee. So these should be okay if the system is fast enough, and then you have this, you're still fine. But if you're sending something, for example, to Mars, then you cannot allow, like, you have to have 100% guarantee. So the soft real-time systems would not be feasible in that particular case.